Hello, everybody. My name is Sean Morrissey. I'm an electrical applications engineer at Alpha Omega Product Development Systems. And today I'm going to be showing you how to design a Wilkinson power divider in the circuit tool within AEDT. For those of you who don't know, Wilkinson power divider is a very common power divider circuit used throughout RF and microwave circuit design. It has this resistor between the two output ports, this being the input. Um, this resistor allows complete isolation between the two outputs, which is really useful in RF communication systems to be able to prevent crosstalk between channels. So very common power divider to use. Also, reciprocally, it can be used as a power combiner if you input your signal in the output. Yeah, make your output your inputs, and then that way it's a combiner. For this tutorial, we're going to be using the circuit tool as opposed to HFSS because I believe that is a very good and useful tool to get familiarized with, especially as a design engineer. I think that the circuit tool should be used in conjunction with the with HFSS as it can help produce more accurate results for your projects. So with that, let's get started. So here, open up your Ansys Electronics desktop. Make sure you are in the desktop ribbon, and we are going to go to Circuit, Insert Circuit. I'm going to click OK. And then here, you can see not too much has changed within your UI here, except instead of the geometry window, we have schematic for you to be ready to design your circuit on, and then also your component libraries. I do recommend going through the circuit libraries as there's a lot of pre-generated components and symbols that will be good for your project. Specifically, if you wanted to, you could go to Ideal Microwave and you could go ahead and grab a power combiner divider, and then this tutorial is complete for you. But if you need to make a more customized circuit or WPD focus power divider, then this tutorial is for you. So let's go ahead, let's get started. First step, menu bar, go to circuit. You want to go to TRL, microstrip, single. This is where we're going to be creating our substrate and assigning its material characteristics. So you're going to go to new. To stay consistent with my previous videos, we're going to do Rogers RO. I'm sorry, no, 4350. 0.15 millimeters, again, to stay consistent. My epsilon R for this material is 3.66. The loss tangent is 0.004. You can keep HU to be the same. And then from here, you're going to press OK. And now, of course, you can change these material characteristics to be whatever matches the scope of your project. But if you're following along, keep it just as I did. Press OK. I'm going to press OK again. And here, microstrip calculator pops up, and this is a really helpful tool that Ansys has integrated into the circuit tool, where W is your microstrip width, P is the physical length of your microstrip line, Z naught is, of course, your characteristic impedance, and we will be using 50. E is your electrical length. Let me bring up the diagram from Posar again. For simplicity, I've made the length of our input port line to be 3 millimeters, which will, of course, match our output port line lengths. This is just an arbitrary small value. You can have it be, again, whatever matches the scope of your project. For this example, I'm going to be using 3 millimeters. So for this first calculation, all we're really looking for is the width. And as I stated before, our characteristic impedance is going to be 50. So let's drag that back over here. We're going to keep this to be 50, leave that at 45, and we're going to use 10 gigahertz to, again, be consistent with previous examples. So 10 gigahertz, and we're going to synthesize. What the synthesis will do is that it will take these values and go ahead and calculate our width and our length on this side. Now, inversely, if you have the width and the physical length of your microstrip line, you can insert those values here, insert your frequency, make sure you change your units to match what you are actually entering. And then you hit analyze, and it'll give you the calculated characteristic impedance and electrical length as well. So here, I'm going to synthesize and get 0.31 millimeters for our width. And again, we don't really want to pay any attention to our length, as I have it as a fixed value of 3. The calculation that we just made is going to match these microstrip lines, this first input, and then the ones directly connecting to our ports actually is what we can call them. So this line, and this line are all going to have a width of 0.31 millimeters and 3 millimeters length. Now the calculation for where the path actually splits is going to have a different width and length. So square root 2 of 50 ohms is going to be 70.7, and then these are going to be a quarter wavelength apart, so we know our electrical length is going to be 90. So let's go ahead and change those. 90, and this is 70.7. And we want both width and length here. So we're going to press synthesize again. We get a width of 0.16 millimeters and a length of 4.62 millimeters roughly. So with that, we're going to close out of the calculator there. And although it's gone now, it is important to note that it already had input, or it already had inputted the material properties of our substrate. So starting off, let's grab some transmission lines. You're going to go to distributed, microstrip, transmission lines. We're going to grab physical length. We're going to go ahead and match the design of the Wilkinson power divider, where these 3 transmission lines are at the ports, and these 2 transmission lines are what we just calculated where the signal diverges. So the one thing we're missing now is a resistor. So back in the component libraries, you're going to go down to resistors and just grab generic resistor. You can press R to rotate it, fit it between. There we go. And just to make this a little bit prettier, I'm going to go ahead and move this 50 out the way to be just a little bit more readable. Now you're going to click on these little square boxes here, and it's going to automatically start drawing a line for you. Now you just lead your components to one another, as with any other schematic tool. Now the one thing we're missing are our ports. Make sure you match these port numbers to match your circuit design as well, and not just arbitrarily place them. Things can get a bit messy if you do that. But from here, the only thing we have to do now, let me to center that, make these a little bit more readable. Okay. Now we got to change our values with these transmission lines here being the same width and length, and we calculated those to be 0.311. Don't forget your units. And then here, this is going to be the predetermined value of 3 millimeters. So we're going to go through and change these. There we go. And so now same for here with the final calculation we did. This was 0.16 millimeters. And this length was calculated to be 4.62 millimeters. 0.16. Don't forget the units. 4.62 millimeters. Great. And so our resistor value is going to be 2 times our characteristic impedance, which is going to be 2 times 50, and that is 100. So here our circuit is complete. And so now what we have to do is add our solution. So you're going to go to Add Nexum Solution Setup by right-clicking on Analysis. You're going to go to Linear Network Analysis. Click on Add, and you're going to change this setup to be a linear step. From here, it's going to be the same window. I'm going to press Cancel just to show you how from a previous example, this was set up. So linear step. I had started it at 5 gigahertz, stopped it at 15. Since my solution frequency is 10, I made it the center. And then you want to make sure you have a pretty refined step count. So you're going to do 0.01 gigahertz, and then you're going to click Add. Since mine's already in there, I'm not going to press Add. But this is what you would do. You would click OK, and then you click OK again. You get your linear frequency. And so now this should not take long at all. It should only take a few seconds for you. You're going to hit Analyze. Make sure no errors pop up. Yeah, matter of seconds, it's done. Should be the same for you as well. You're going to go to Results, Create Standard Report, Rectangular Plot. And from here, we're just going to want to take a look at all our S parameters. I'm going to click on New Report. And as you can see, each graph is color-coded. If you want to look at a specific one, you just click on it. However, here, let's exit out of here. We can see that our S11, this red line, is perfectly at 10 gigahertz. Now, that's, of course, because this is an ideal Wilkinson power divider. But say if you want to check your values, you can go to Modify Report. And instead of dB, select all of them. You can select the magnitude instead. And you can create a new report, which gives you all the magnitudes as well. So with that, that is how you design a Wilkinson power divider in the AEDT circuit tool. Thank you so much for watching.